Okay, hello, this is Dr. Muhammad and this is another video under design of steel structures according to AISC, and we are going to talk today about compression members part 3. In today's video I'm going to talk about the design of columns, which is going to be mainly related to the steps of design, and I'm going to give a couple of examples that is going to provide for us good understanding for the main steps of design whenever that you are going to design a compression member. Okay, now let's go directly to the design steps and to know more about them. Before going into the design steps, I'm going to give some hints, general hints about how to go through the steps of design. The selection of economical rolled shape to resist a given compressive load is simple with the aid of the column load tables. This means that we have different types for the or different ways for the design, but column load tables are going to be the most effective way. So we are going to enter the table with the effective length. So now the first thing that we need to put in our mind is we need to get KL, which is the effective length. So we need to know what is the end condition of our column and what is the length of the column, and then we can obtain the effective length. And then we're going to move horizontally until you find the desired available strengths. Again, we are going to move horizontally because we are using the column load tables. So you need to get KL and then go horizontally until you find the desired available strengths, whatever the type, or something slightly larger. This is the way, as we are going to see in the examples. Okay. In some cases, you must continue the search to be certain that you have found the lightest shape. So the second challenge here, not only to obtain the desired available strengths, also you need to take care of the lightest shape that you could or that you should have. Okay, that is going to provide the desired available strength for you, but with the least cost. Usually the category of shape, which is wide flanges or T from the wide flanges, etc., will have been decided upon in advance. Means that the cross section itself, the height itself, for example, or the width, which is going to be, these are like the dimensions of our cross section. They are going to be decided in advance, okay, based on the architectural requirements and so on. Often the overall nominal dimensions will also be known because the architectural or other requirements, as we said. As pointed out earlier, all tabulated values correspond to the slenderness, to a slenderness ratio of 200 or less. This is another point that we need to take care of. Slenderness ratio, KL over R, which is the maximum, okay? The maximum slenderness ratio should not go beyond 200, as we said. And you are going to find in the table that it is ended with some solid lines there. The tabulated unsymmetrical shapes, okay? The structural T's and the single angle, double angles require special consideration and are going to be covered later. So we are going to talk about the symmetric shapes. Okay, for today we're not going to be exposed to the other unsymmetric or unsymmetrical shapes. For shapes not in the column load table, sometimes we can face a situation where that we cannot find our shape in the column load table. In this case, a trial and error approach must be used, as we are going to see. Okay, I'm going to give an example that is going to explain about this point in detail. The general procedure is to assume a shape. So we're going to assume like shape and then compute its strength, the corresponding strength. If the strength is too small, it means that it is unsafe, or too large means that it is uneconomical. Another trial must be made. Okay, a systematic approach to making the trial selection is as follows. So this is the steps of the design, okay, commonly that we are going to use. So first of all, we are going to assume a value for the critical buckling stress, which is FCR. We are going to assume it. Okay, we're going to assume it. Examination of AISC equation E3-2 and E3-3 shows that the theoretically maximum value of FCR is yield stress, right? Do you remember when we were like talking about the elastic buckling and inelastic buckling? Do you remember that we said something like this? Here it was F yield, right? And then there is a limit here. Okay, this limit is going to differentiate between the elastic part and inelastic part. So now you are going to guess, or you are going to like assume this FCR. Okay, so you are going to assume the upper limit is F yield. Then if you are going to assume and start with FCR, then you can, like, let's assume that FCR, for example, equal to 2/3 of F yield. This might be a good start for you. Again, you are going to refine this later, okay, based on the steps that we are going to talk about now. But again, this is only an assumed value in the beginning. The accurate one is going to be obtained during the steps. And number 2, determine the required area. So number 2 is the required area. Step 1, assumption of FCR. Step 2 is the determination of the required area. Simply, we have two approaches, one for LRFD and the other is for ASD. The area gross should be larger than or equal to P ultimate over phi C times FCR. Actually, it comes from our famous equation. Phi C times FCR times area gross should be larger than or equal to P ultimate. Okay, and for the ASD, it is also coming, our equation, or the area gross should be larger than or equal to the right hand side of it, which is coming from the famous equation that is 0.6 FCR, which is the allowable stress should be, the allowable stress should be larger than or equal to P actual, or the applied load, over area gross. So from here we can get area gross. Okay, so this is the second step. Okay. The third step is select a shape that satisfies the area requirement. So what we have obtained, whether that for LRFD or ASD, we are going to obtain or to get or select a shape from the tables. Okay, and after that, step 4, we are going to compute FCR and the strengths for the trial shape. Remember that FCR already we have assumed it here and like step 1, but again it was like an assumed value, but the actual value is going to be computed. Compute FCR and the strength for the trial shape. Okay, then if you were lucky, then you're going to find that your assumed FCR equal to the computed FCR. If not, which is the common case, you're going to make another trial. Okay, and step 5, it is going to be related to revision of what you have done. Revise if necessary. If the available strength is very close to the required value, the next tabulated size, take care, this word is keyword here, next. Go to the next. Next tabulated size can be tried, okay? Or you can change the FCR, the assumed FCR, for example. Okay, if you have here FCR that is very small and you have like assumed FCR to be very large, then you can like halfway through would be like maybe your new assumption and you are going to make another trial. Otherwise, repeat the entire procedure. Okay. Using the value of FCR found for the current trial shape as a value for step 1. So we're going to start with FCR again. We're going to go to step number 1 again and repeat what you have done. So here it requires some guessing from you until that you reach to FCR. FCR is considered to be like the critical. It is the critical component in the design process. Okay, if you could guess it well, then it will be okay. If not, then you're going to spend some time on trial and error process. And then the last step is going to be check local stability. It is the last step, which is the width to thickness ratios for the flanges, for example, if it's necessary, or the height to thickness ratio for the whips, okay, if it's necessary. Okay. Now let's go. I think that we are ready now for our design for the example, in order to know more about the design steps. Okay, let's go for the example. Okay, the first example is like this. Select the lightest wide flange shape that can resist a service dead load of 62.5 kips and a service live load of 125 kips. The effective length is 24 feet, and we are going to use ASTM A99 steel. Okay. The appropriate strategy here is to find the lightest shape for each nominal depth, okay, in the column load tables, and then choose the lightest overall. Actually, the strategy here is going to be built upon what already given in the example. The example is talking about lightest, and is also talking about the wide flange, okay? Lightest wide flange. So then we are going to the table, we are going to the column load tables, and then we're going to investigate, okay, the lightest shape for each nominal depth. You are going to find in the table different nominal depths. You're going to start with from 8, for example, then 10, 12, 14. Okay, this is the nominal depth. It is like increasing here. You are going to find 8 in the bottom, and then after that you're going to above it 10, and then 12, 14, and so on. Okay, then we're going to check what is the lightest in each nominal depth, and then we're going to compare all of them. Okay, we're going to compare all of them, and the lightest overall is going to be considered. Okay, so our strategy for the solution is two-step strategies, like investigating the lightest shape for each nominal depth, and then we are going to use the column load tables to choose the lightest overall. These are the two strategy solution. Okay, so now let's go and put our example in a way that we can use, in a way that we can solve it. So first of all, we have the service live load and dead load. So we have the ultimate load. If we're talking about LRFD, we're going to design first based on LRFD. Then our factored load is going to be 1.2 dead plus 1.6 live. As we said, this is the governing equation, or the governing load combination for us commonly, as long as there is no wind loads or earthquakes. The value of the ultimate load is going to be 275 kips. From the column load tables, which is table 4-1, we're talking about wide shapes here, or wide flanges. So the choices are as follows. We have, as I said, this is the nominal depth that can be found in the manual. Please stop the video here and go to your manual and check what I'm saying here. Okay. Then we're going to find that we're going to investigate first the wide flange with the nominal depth of 8. Okay, sorry. So here, this is the table 4-1, which is the available strengths table for 50 KSI wide flanges, and the depth is nominal depth 8. It is given already for us. Okay, then we are going to check, as we said, the lightest one. Here it is the weight per unit length. So we are going to start from right to left, going from right to left in the table. Open the table, open the table. Okay, now you're going to find that it is 31 here on the most right. After that, going left to 35, 40, 48, 58, 67, right? Then for each one, start with 31. Remember that our required or ultimate load is 275, right? So if we could reach something equal to 275 or more, then it's okay. Less is not okay, not acceptable. So now here for 31, this is for LRFD, we are going with the KL, we're going with the KL, our KL here equal to, let's go back, our KL is given, which is the effective length 24, right? So we need to go KL, which is 24, okay? And we are assuming that it is with the respect to the least radius of gyration, which is Ry. We know this. Okay, we're going to read from the right. Under W8 times 31, the strength is 101, which is not acceptable. It is less than 275. Then go to 35, it is 115, still less. Here for 40, it is 133. For 48, it is 166. For 58, it is 205. We are closer now. And then for 67, I mean that W8 by 67, it is 241. Is there anything else? No, there is nothing. I mean that the wide flange with depth 8, W8, it doesn't have this kind of strength needed. Okay, so all the shapes, okay, all these different shapes are having phi c Pn, which is the available strength here for axial compression, less than 275. So we cannot use this cross section. Okay, so let's go back and put it. So there are no wide flanges with depth 8 with phi c times Pn larger than 275, so we're going to exclude this. Okay, this section won't work for us. Okay, now let's go to the next section, which is W10. Okay, let's go and reach and try to find. So we're going to find W10. Please stop the video and go to your manual. Okay, I'm repeating it many times because it is really important for you to do what I'm saying. Okay, if you're not going to do it by your hand, if you're not going to browse your manual, you're going to find yourself not familiar with what I'm saying, and you're not going to be familiar with using the tables. Anyway, this is for W10. We're going, as we said, from right to the left. Here at 33, we found that it is 99.5. For W10 by 39, it was 122. Still, we are talking about LRFDs, okay? LRFD columns. That's it. So here also 146, 254. Okay, here it is 282. It is larger than 275, right? So this means that we can use this. We are talking about 224, which is KL, our KL. Okay, so now for this nominal depth, W10, it was 282. Okay, let's record it in our example. So for W10 by 54, this is the weight. Go back here. It is 54. Okay, it is for 54. W10 by 54, it is going to be our section, and phi c Pn for it, available strength, is going to be 282. Okay, now we said this is not working, this is okay. Let's go to W12. Okay, for W12, for 24 here, and let's go from the right to left as we have said. It is 120 here, 136, 153, and so on and so forth, until that we reach 261. Still we have 275. This is our limit. Now the next shape is 293. Okay, so our wide flange 12 by 58 is going to provide for us this value, which is 293. Okay, so let's go and record this. W12 by 58, it gives us available strength of 293. And then the last, then we said this is not working, this is working, this is working now, and let's check W14, which is the last one. For W14, for KL equal to 24, starting from the right to the left. So for different sections for LRFD, 123, 140, and so on, until we reach to this value, 293 at 61. This means that our section going to be wide flange 14 by 61, and it is going to provide for LRFD design strengths or available strengths for the compression member 293. Okay. Is there any other sections? No, cannot find anything else. Okay, these are the available strengths in the column table. Okay, the column load table. Now let's go and record it. So for W14 by 61, it was 293. Okay, how we are going to use this, how we are going to compare? We said that W8 is not working. All of them, W10, 12, and 14, for these shapes, they are working. And all of them, they are providing, okay, higher than all of them, they are higher than 275. So all of them are okay. So we are going to check which one is the least in terms of the weight. The first section, the weight is 54 per unit length. Here 58 per unit length. Here is 61 per unit length. So we are going to use the least one, which is exactly W10 by 54. And this is our final design section. There is something that we need to take care of, which is note that the strength is not proportional to the weight, which is a function of the cross-sectional area. That's right. It has nothing to do. The strength has nothing to do with the weight. Okay. So do not say that. Because, for example, here the weight is 58, here the weight is 61, okay, but here the two strengths are the same, right? Why? Because the cross-section distribution here for this and this, like, utilizes this 58 in a way that is going to give the same strengths as the 61, the weight of 61, okay? So this means that here W10, it is the least weight, and it has a very good strength, which is larger than 275, and it is the least, so it's the most economic for our case. Okay, so we're going to use it. Then we're going to repeat the same, but for ASD. So now let's go to the ASD solution. Okay, we're going to repeat it, and I'm going to go through it rapidly, and I'm going to show again the tables. It is already, we have it. So for the actual or applied load, it is dead load plus live load. This is the critical load combination for ASD. And after that we have 188. This is the applied load. We need our available strengths to be higher than this. From the column load tables still, the choices are as follows. Let's go through what we have done before. So W8, let's go now to W8 again. Already we have done it before. So W8, and if you go, remember that our limit is 188, the allowable strengths, the applied strengths 188 kips. If you go here by looking to this line, you're not going to find anything related to ASD. Look to the maximum even here, which is the highest one. It is, look here, it is 160. So this means that this cross section would not work for us. Okay, now let's go to the next, which is W10. Go to 24 KL, going from the lightest, as we said. Remember, 188. So here, if you go 66, blah blah blah, here until we reach here. It was ASD 169. Here it is 188, exactly as we want. So this cross section is going to be our cross section here. It is going to be W10 by 54. W10, okay, by 54, and it is going to provide exactly the same value, 188. Now let's go to the W12 for 24. and then going from the right to the left, but taking the ASD columns here. Every time we're going to have the ASD columns here. We're going to find that going here until ASD, here it is 174 here, which is for W12 by 53. The next one providing us 195, which is 58 also. So this means that W12 by 58, it provides for us available strengths of 195. Okay, so now let's record what we have done for the ASD. This is W10 by 54, W12 by 58, W14 by 61. It is similar as the LRFD, and the provided strengths for each one are going to find still this cross section, which is W10 by 54. It is the most economic one, and we are going to use it. Okay, as we said, this is the lightest cross section that we should use. Okay, I hope that we get familiar. Please go to your manual again and do this example by yourself alone, okay, without looking to the video, and you are going to get benefit from going through and browsing through the manual. Okay, now let's go to the last example, or the second example for us, which is going to be a real design example that is going to have some trials. Okay, so let's see how we can deal with this. Okay, now here the example is given like this. Select a white flange with the depth of 18. So it is already given for us, the white flange, and the depth is given for us, okay, which is 18. The shape is A 99.2, means that our F field equal to 50. That can resist a service dead load of 100 kips and a service live load of 300 kips. The effective length is 26. That's important. Okay, KL, our KL equal to 26. Okay, now we're going to use, as usual, LRFD and ASD. We want the ultimate load applied. It is, as we said, the load combination. It is going to be 1.2 dead plus 1.6 live, which is the critical load combination as long as there is no lateral loads like wind load or earthquakes. 1.2 times 100 dead plus 1.6 times the live load, which is 300. It gives us 600 kips. Okay, now if we're going to start with the steps of the design. Do you remember the first step? The first step that I have explained before, it was assuming FCR, okay, the critical buckling strength of the element. So we are going to assume FCR to be 33 KSI. Why? Because if you look, we have F field for this. We have F field, as we said, equal to 50. So our FCR is going to be like 2/3 of this 50. Okay, this gives us 33. So we're going to start with an assumed value. Again, it is an assumed value, which is 33. Okay, it is 33. Okay, and now we are going to the second step, which is the required area gross. It is going to be P ultimate, which is already given for us, over phi C times FCR. Okay, this is the available strength for LRFD, and we have phi C, it is 0.9, as we know. FCR, this is our assumption, 33, and here this is 600. So we need 20.2 inch squared. Okay, we are going to the table. We're going to the table with W18 and try to find something, any shape that is exceeding this 20. If you go to the table, you're going to find, if you are going to the table, you are going to find that W18 by 71 is going to give to you area gross equal to 20.8, which is larger than this, slightly larger than the required area gross. Please go to the manual now. Stop the video and go and check this value. Okay, area gross. Go to the dimensions and properties table and check this value right now. Okay, after that, this is the area gross. We're going to obtain what is KL over R. KL already given for us, which is going to be 26. This is an foot. We're going to multiply by 12 to transform it to inches over R minimum. What is R minimum here? R minimum for wide flange 18 by 71. You can obtain it from the table. So go and obtain this value and check that it equals to 1.7 for the wide flange 18 by 71. If you check this, you're going to find it 183.5, which is less than our maximum slenderness ratio, which is 200. So it is okay now. The area gross and the slenderness ratio are okay for us. The last thing is what? Exactly. We want to know what is FCR, the real one. Remember that we have assumed it here. It is assumed. Okay. We need to get the real one based on our real cross section. So if you remember, we want, if the FCR is here, we want to, if you remember, make the two parts of elastic and inelastic buckling strength. Go 2 videos back and I have explained this in detail before. So, and we have a limit here. This limit is going to be exactly on the slenderness ratio. It is going to be 4.71 times E over F yield. Okay, this is KL over R here, and this is going to be our FCR. Okay, so we are going to see whether that it is elastic buckling or inelastic buckling. Okay, because every side has its own equation that is going to govern our FCR. When we check this, you're going to find that in order to obtain, this is our limit, which is E over F yield. E, it is 29,000. It is constant for all types of steel. And over F yield, which is 50, because we use a 9092 type of steel. And this is 113. Okay, this is our limit. So the limit here is 113. So what is our KL over R? It is 183, right? 183. Okay, so in this case, our KL over R, our KL over R, which is already, we have it 183 here. Okay, this is the value that we have used, KL over R. It is larger than the limit, which is 113. So we are going to use AISC equation E3-3. This means that elastic buckling. And in the elastic buckling, if you remember, our FCR equal to what? Exactly 0.77 FE, Euler strength, okay? And this is going to be calculated. We need to calculate this FE. So FE, if you remember, FE equals to pi squared E over KL over R to the power 2. From where I got this? From the previous videos. Please revisit it. Okay, so we are going to obtain this FE. This value of FE is going to be 8.5 here. This is 8.5. Then we're going to substitute in this equation to obtain our FCR, which is the real available strengths, buckling strengths, critical buckling strengths for our shape, for this shape. So in this case, we are having FCR. After substitution, we found that it equals to 7.45. Can you imagine this? It is so far from the assumed value. The assumed value was 33. We started with 33. If we go back here, 33. This is, we tried it only, like 2/3 arbitrary choice of 2/3 of F yield, right? But the one that we have obtained, it is 7.45. Very far, okay, so far from the assumed value. Then let's go and calculate phi c times Pn. Our phi c, it is going to be 0.9, and FCR, which is already 7.4, we have obtained it, and the area gross already we know it from before. When you calculate this and multiply, you're going to find that the available strength or the design strength for this is going to be 140 kips. The design strength of this cross section is going to be 140 kips. However, that the applied one is how much, or the ultimate one that we have calculated is 600 kips, right? It is so less than our ultimate load. This means that our trial, our first trial, is not going to work for us. Okay, we need to go to another trial. We need to go to another trial. Okay, there is a hint here. Our calculated FCR is so far from the 33, right? So this is why you're going to find that the strength here is so less than the required ultimate strength. Okay, because the initial estimate of FCR was so far off. Assume a value. In this way, we need to assume a value in between. So now we have 7.455. This is for FCR. And the other value that we have, 33, right? Now, this is the one that we have obtained from our trial. And this is the one that we have assumed before. Let's assume something in between. Like, for example, let's take it 20 KSI. Okay, 20 KSI. In this case, we are going to assume this 20, and we are going to obtain area gross again. P ultimate over phi c times FCR, which is times 20 here, it is going to give us 33.3. Let's go to our table and try to find another shape other than this shape that is having area gross larger than 33.3. Okay, so now this is the second trial for us. This is the second trial. Go to your manual and try to find area gross larger than 33.3. And you're going to find this W18 by 119. This gives you, this section is going to provide 35.1 inches square, which is larger than the required area gross. Again, repeat the same process again. KL over R minimum for this shape. This is from the properties table. KL, it is already given for us. Then we're going to obtain 116, which is less than the maximum slenderness ratio. Area gross okay, stiffness requirement is okay. Now let's go to the FCR. We want to check what is FCR for us. Again, for FCR, we need to calculate whether it is for local buckling, for elastic buckling, or inelastic buckling. We need to obtain Euler stress, okay? Critical stress. So it is going to be pi squared E over KL over R. Here we are going to put 116, which is KL over R minimum. It gives us 21.27. We are going to use it for the calculation of FCR later on. But now we want to know where exactly our equation, elastic buckling or inelastic buckling. So we want to obtain this limit, which is 4.71 square root of E over F yield. Okay, this is the slenderness ratio here in the horizontal axis, as I've explained it like 2 lectures before. Okay, so this means that our KL over R should be, it is larger, not should be, sorry, it is larger because already we have 116 here. KL over R as the limit, the proportional limit here, the limit between elastic and inelastic. We found it. It was 113 from the previous calculation in the previous slide. So this means that our equation is still in the right side here, which is the elastic buckling. So we're going to use 0.877 FE. FE already we have calculated before. Then we are going to obtain FCR 18.65. And the available strength in this case is going to be phi c times Pn, which is phi c times FCR that we have obtained, which is 18. area gross that already we have calculated before from here, then it gives 589 kips. Very close, right? It's very close to our original, okay, original ultimate load. But still it's not good, but very close. Means that our assumption from the beginning, okay, our assumption was okay. Our assumption was okay. Remember that our FCR, it is 18.65. Do you remember what was the assumption that we started with? 20. Let's go back here. 20 KSI. We assumed this. So the next trial was 18.6. So it is very close to our assumption. FCR that we have assumed is very close to the calculated FCR. This makes our available strength is very close to the required ultimate strength. Okay. Now, what is the next step? Is we're going to into the last trial, which is next larger size, next a little bit larger size, larger than this. So we are sure that only one larger size is going to make it higher than 600. Let's go to the larger size. This is trial number 3. So after it here it was 119. The next one is 130. W18 by 130. The same area gross from the dimension and properties table. Stop the video as I said and go and check what I am saying. KL over R minimum from the dimension and properties table. It is 115. Less than 200, it's okay for stiffness requirement. Then after area gross, after the slenderness ratio, we need to calculate the FCR. This is our third step. So these two here, it is related to calculation of the FCR. To see where that we are in the in the elastic or inelastic buckling. So our KL over R, it is 115. And our limit here, as we said before, it is 113. This means that still we are in the elastic buckling zone. This means that our FCR is 0.877 FE, which already we have calculated, but here put 115. Okay, it is function of the KL over R of the section. Then FCR is going to be 18.75. Okay, 79. In this case, when you calculate the strength with this 18 and the area gross that we have here, you're going to find that it's 646, which is larger than our ultimate load, required load, which is okay for us. Okay, this shape is not slender. Okay, our shape, this is the shape here that I'm talking about, which is wide flange 18 by 130. It is not slender. Who says that? Because there is no footnote in the dimensions and properties table to indicate that it is. Okay. So what is the meaning of this? Local buckling does not have to be investigated for this section. Okay. Local buckling does not have to be investigated for this section. Let's have a look on the table here. This is the dimension table. Okay, and this is the shapes that you are going to check. You are going to find that for W18 by 130, you're going to find that there is nothing here. There is no like designation or superscript that is giving you C. For example, look here to this shape, for example. There's C here. This means that there is a problem for this. Not problem, it means that it is going to be slender. Okay, local stability going to be an issue for this table, for this cross section. Okay, in general, this cross section is going to have some stability issues. Okay, so if you are going to use like 422 table, for example, this means that you need to take care, that you need to consider the local stability issues. Okay, but for 4-1 it is okay. For table 4-1, no problem. It is going to be already, the strength is going to be reduced already. Okay, and here we're going to find that for W18, as I said, by 130, there is nothing related to it. There is no superscript here. But for the C, for example, here, it is given the shape is not slender. Okay, in our case, because for the C, as it is written here, C shape is cylinder for compression with F yield 50. Okay, our F yield here, it is 50. So if this cross section, for example, is going to be used, we're going to find C here. Okay, this means all of them, they are having problem with local stability. Okay, I hope that you have understood how to use the tables in using our technique for the design of columns. What I want you to remember, that we have like fixed steps for the design of columns, which is 6 main steps. Please memorize them very well and try to work the 2 examples again that I have given to you. Okay, and try to work them without looking to the materials or to the video. Work them by yourself and try to go through them. Okay, again, this is the end of this video. I hope that you have understood, and I hope that you can work your own way for, or at least you can do what I have explained today for designing your own columns, whether for your project or for whatever that you are pursuing. Thank you, and see you in the next video.